so this talk is going to be about how natural language processing motivates why it works and how deep learning is working in the field. I figured a lot of people like to open their laptops and click around on maybe concepts I introduce. So the slides are also at my GitHub if you like. Could everyone read it? Cool. I see someone. Cool. So it's going to be about natural language processing and how deep learning or how machine learning in general is being used in processing language. First, I'm going to motivate why. Why care? Why do we care about natural language processing, and moreover, motivate why machine learning seems such a good idea? It turns out that a lot of the examples I will give, there's a specific algorithm being used, which are recurrent neural networks. So the second part is going to talk about how we structure them and how they work. And finally, I figured in this conference it's PyData, so a lot of people might not be interested in machine learning, but also in Python and how we employ and deploy models. So the third part will cover, hey, how do we train this? Use case is going to be Google Translate. Or if you Google and you care about 26 languages, how do you train a model? And if you Google and you care about translation within a second, how do you make fast inference? So who here uses Gmail on their smartphone? I've seen this function before. This is what I find a good example of natural language processing. A friend might email you and say, hey Rob, do you want to come over for a barbecue this weekend? And this algorithm automatically proposes a reply for you. It says, hey, count us in. Or it says, hey, no, sorry, I'm not in for the weekend. Another example is the speech recognition engine Siri by Apple. Who here uses Siri by Apple? So what it does, it okay, more Google users than Apple users in here. So it automatically processes your queue. You can say, Siri, show me the phone number of my mom. And it will process this queue and prompt me the phone number of the person I asked for. Another example of natural language processing, we do question answering. We can look at images or we can look at other text and we can answer a question. What colors are the bananas? And the algorithm, the natural language processing algorithm, will answer for us, hey, these bananas are green. The fun thing about the last thing is that we're also going to cover attention models, and you can visualize it. So this algorithm somehow understands how we as humans process language. When we ask it what is on the what is the fur on the cat's tail, it will answer for it. It will put attention exactly on the cat's tail. And you can also do reasoning. Actually, you can read a story. Algorithms can read stories and answer questions on top of that. But the main focus for today in natural language processing is going to be machine translation. We care about translating as an English sentence to a French sentence. This is a fun image I found on the Microsoft research blog recently, where they kind of show what deep learning is doing in is machine translation. It kind of flattened, and now we are given this new leap. This is the translation I care about. And then also to kind of orient us a bit, where are we in the field of AI, of machine learning? This is how I see the world. I mean, you might have different views, but to kind of orient us in all these algorithms. Machine learning, we have supervised learning because we have data, we have English and French sentences. We care about natural language processing, and deep learning is going to be our tool for today. I also want to say that I want to make this talk interactive. Yes, in the end, there's 10 minutes for questions. But if at some moment you kind of lose my explanation, please raise your hand. No. So in all those examples I showed you so far, there's one overlapping theme. Is that all the recent innovations and all the recent breakthroughs are made with one specific algorithm, which is a recurrent neural network. So this part, we will discuss how do recurrent neural networks work. What is in our intuition for why they are used for language, and how do recurrent neural networks work. So who here is familiar with normal neural networks? Who here trained a neural network before? Cool. So to get everyone on the same line, a neural network is inspired of the brain, where one neuron activates another neuron, activates another neuron. We might have an input, say an image or text, and then the neurons in the end, we say, hey, that might be a class, like cat or dog, or in our case, an object or a subject, or in a sentence. We might also depict the neural. Oh, so we're at PyData. This is the bare Python code for a neural network. We have an input x. We map that to hidden neurons, to hidden states h, and we map that to an output. And our neural network is just these basic lines of Python. We could also depict that in images. So we map one vector to another vector. But now let's say we care about classification of objects, verbs, and subjects. So in this, our neural network would say I is a subject, kick is a verb, the ball is an object. In the second sentence, it would say the ball is a subject, rolls is the verb, and away is the object. But something will not quite work in here. In the first case, the ball was the object, and the neural network would then classify this as an object. But here it is a subject. So how would the neural network distinguish between the two? And that is where a recurrent neural network comes in. We can connect all these neural networks over time. Because if the neural network would have access to the classification it made before, then it can know. It would learn, hey, if my previous word was a verb, then probably this is an object. And if I had no previous word, maybe, then this might as well be a subject. So we have lines between here. That is the recurrent neural network. Again, these are the equations, but I figured many more people here read Python code. This is now the bare Python code for a recurrent neural network. The difference is we are passing on this h. The hidden state now is an instance variable of our recurrent neural network class. Quickly compare it. So this is not a full code, but this is the meaty part of the code. Here we calculate this h, and h maps to the output. Yet in a recurrent neural network, information recurs over time. So we have a self.h. So the self.h of the old time step and the input together made the new self.h, and that maps to the output. A recurrent neural network. So now this hidden state, it will learn. We can train this neural network. And now this hidden state, it might propagate information. Hey, this was kind of a verb. Possibly this is an object. Here there's no input information, so a neural network might learn, possibly, or very probably, this is a subject. And to show you that this is the basic recurrent neural network and it works, in here this is a clickable link. If you open the slide, you can click on this and you will see an implementation of a recurrent neural network in 112 lines of Python code. We can already do powerful things with this setup. You can think about weather forecasting, where you're inputting input vectors about the weather and you want to predict tomorrow's weather. We can do powerful things like detection of what a user is doing with the smartphone. Is he running? Is he walking? Is he taking the stairs? So input vectors would be the accelerometer data and output would be walking. I think 2 times over the weekend I talked to people from the financial markets. In financial markets, we're actually interested in predicting other stocks based on information from one stock. So input can be information about some stock, and output can be information about another stock. You see the applications going. One thing that this model won't do for us is that we are kind of restricted that at every moment we have to make some classification. So input and output are aligned. But if you think about it, for machine translation, no such thing works. If I translate between English and Dutch, maybe. But what now if I translate between English and Chinese? Then there's no such alignment of input and output. So we need to come up with a different architecture of a recurrent neural network that deals with a different sequence of input words than a different sequence of output words. And that gets us to the sec-to-sec architecture. Who here has seen the abbreviation sec-to-sec before? Yeah. It abbreviates for sequence to sequence, Because in our new architecture, we care about mapping an input sequence to an output sequence. And in this case, the recurrent neural network can work with any length of sequences. Now, the input sequence can be 5 tokens, and the output sequence can be 4 tokens. So then, this first part, we name that the encoder. It cares about encoding the words of the input language. And this part, we call it the decoder. It cares about decoding the words of the output language. So let's take a step back in the conversation we had so far. What did we do? I started with motivating natural language processing. I said natural language processing, and I gave some examples like the translation or the Gmail reply. And then we said, okay, we're going to look at recurrent neural networks. Recurrent neural networks because they allow us to deal with machine learning algorithms over time. And now we are extending that toward a sequence-to-sequence architecture, wherein we say we split our recurrent neural network up in an encoder and a decoder part. And that way we can work with input and output sentences of different length. To this model, I'm going to add one more detail before we're going to continue on how do you train these models. And the problem is as follows. Let's say I have a very long, as long as it fits on my slides, input sentence, and I want to map it to an output sentence. Maybe the input sentence has kind of a special word or has kind of a hard word. Now the recurrent neural network will have a hard time on remembering the specific word. Maybe Tuinstraat it's a Dutch street name, and it might be hard for this recurrent neural network to encode. So by the time we are translating this French language or this French sentence, we might have forgotten about what was Tuinstraat. How would we solve this as humans? What would we do as humans if we were translating this English language to a French sentence? We would peek back, right? If by the time we were translating this part of the French sentence, we would just peek back at the input, hey, what were we translating again? And we continue our translation. And a recurrent neural network can do that too, which we call attention. So if the recurrent neural network could give some cue to the encoder, hey, give me again this little piece of information, we forgot the children were playing, but we didn't know which sports they were playing again, then we can kind of peek back at the input. So we have encoded the words les enfants jouent au, and now we peek back at the input and we see, oh, it was soccer. Well, give it input to me, and then I will now translate football. Or I don't know if this is the correct French translation, but I see someone laughing. Maybe it's not, but you get the case. That is attention, and why not do this for every time step? So this is our translation model. In our translation model, we have the encoder. It takes in the words of the input language. And then as soon as we feed the go token, it will start decoding. And at every time step, it gives a key to the encoder to ask for more information. This is the full sec-to-sec model with attention used for translation. You can also visualize it, which is kind of fun, and then you start understanding how attention works. You kind of expect this linear, because English and French are kind of the same languages, so you kind of expect this linear behavior. But the fun thing in here is you see this French off-diagonal stuff. What we do in English is we put the adjective before the noun. What the French language does, it puts the adjective after the noun. And that is this off-diagonal attention you see visualized in here. But that's only a fun thing. We now understand the basic algorithm, or the algorithm. This was actually the algorithm used by Google, right? I mean, this is the algorithm for the machine translation. The second part of the talk is going to care about how do we train this? And moreover, how do we train this under say, some conditions? Because the translation system, it cared about 26 languages. 26 language pairs. So you can I think you can kind of see how many data is involved, how long the training process would be here. So in that respect, we're going to talk about data parallelism and model parallelism, but also we care about fast translation. If you go to translate.google.com and you type your query, you expect your translation, what is it? Between a second, maybe within 100 milliseconds. You don't want to wait for 15 minutes. So we're also going to talk about fast translation. How do we make fast inference? But in the first part, I wanted to focus a little bit on word2vec, because I think as soon as you go into natural language processing, you'll immediately hear about word2vec. Who here has heard about word vectors before? Yeah, a lot of hands. So to get this clear, for the purposes and for the purposes of this talk, we're going to assume that someone gives you a library of word vectors, because what happens is that we have language, we have words, and the Python code I showed you for these neural nets or these recurrent neural networks, they work on vectors. So how do we go from an English word to a vector? And for the purposes, you can assume that someone else did that for you. And now we have a library. We have a library and we can look up every word. We can say, hey, what is the vector for boat? We can look at the table and get a vector for boat. What is the vector for Beijing? And we can look at the table for Beijing. But the fun thing about these vectors is that they have kind of a semantic relation. The vector for China and the vector for Beijing have kind of the same difference vector than Turkey and Ankara, or than Greece and Athens, or Poland and Warsaw. These vectors have also, they also do plural here. So man and woman, or uncle and aunt, or king and queen. They have the same, say, constellation in the vector space, or the same. If you care about linear algebra, the difference vector has the same direction. So king and queens, and king and kings, and queen and queens. Again, this is a clickable link, so if you're interested outside the scope of this talk, but if you're interested in training your own word vectors, you can click this and train your own word vectors. Usually these word vectors are trained on corpora like all of Wikipedia, or all novels, or all articles of the Wall Street Journal. Then people train it for you and you can use their vectors. But now more about training. How do we train these neural networks? Well, the exact weights, they are being trained with gradient descent, with backpropagation. Who here is familiar with gradient descent and backpropagation? Yeah. But because we have so much data, what we can do is that we can parallelize our training over different data buckets. So let's say we have 10 million, we have a data set of 10 million sentence pairs. So we have 10 million tuples of an English sentence and a French sentence. Then what you can also, what we do in here, or what I propose in here, is to split this data up over, say, 10 buckets. So now you can have 10 parallel models training on, say, a million sentence pairs. This neural network are trained via gradient descent. So what you can do is we have a parameter server capturing all the parameters of our neural net. So we send parameters to a bucket and we get the gradient back. And we just update our parameters with our gradients. If you do this asynchronously for implementation details, you can do this asynchronously, and that gives us a huge advantage, because if we do it asynchronously, we are robust to errors in the different buckets. Let's say one of my 10 buckets has an error, or it fails to return parameters, then I can still continue to train on the other 9 buckets. So I can parallelize my data over different buckets. Another option is to look at model parallelism. For model parallelism, what we do is the equations I showed, the Python code I showed you, the equations that govern a neural network are mostly matrix multiplies. A lot of them are matrix multiplies, and we can do them on the CPU, and we can do them on the GPU. So what you care about model parallelism is, can we align all this calculation in a certain way so that we can parallelize our model? To give you Like one example is we have an encoder of the recurrent neural net and a decoder. So if we put the encoder on one GPU and the decoder on another GPU, they can run in parallel. Because the encoder processes a sentence, it pipes data to the. So one GPU encodes the sentence and it can pipe data to the other GPU who does the decoding. But right away, the encoder can start on a new batch. So they run in parallel. We are doing deep learning in here, so we can stack this recurrent neural net to any arbitrary depth. We can also parallelize that. Let's say we have a recurrent neural net of 8 layers. Google Translate used 8 layers of recurrent neural nets. We can run our first layer on one GPU, a second layer on another GPU, and a third layer on another GPU. So that is what model parallelism cares about. You can parallelize your model over different hardware types in order to have it train faster. I don't want to scare you with this part. If you're interested in this kind of engineering problems, you can parallelize the models for yourself. I also want to add that if you use a library like TensorFlow, it will do it for you. So as soon as you fire up a session and you run tf.says.run initialize all variables, then TensorFlow under the hood will say allocate the hardware resources for you. So that's about model parallelism. The final. I kind of switch slides in here. So the final topic in our conversation is going to be about fast inference. We motivated recurrent neural networks. We discussed how recurrent neural networks work. We discussed how we can train recurrent neural networks for machine translation. And finally, we care about fast translation. If you go to Google Translate, you don't want to wait for 15 minutes. You want it now. One thing to do that, and the main trick we are using is quantization. All the operations I showed so far were floating point operations. But we might as well frame them as integer operations, which can be run way faster, which can be run way more efficient. So that is where quantization comes in. We have say the weight matrices and the states in our network. They are all floating points, and if we quantize them as integers, then inference goes way faster. More specifically, if you look at the implementation by Google for their machine translation system, what they did is that they quantized all the states of the network into 8-bit integers, and they quantized all the matrices and say the calculation of activation functions. They quantized it to 16 bits, and that will give us and in that way we can run inference way faster. We can look at the training and see it doesn't hurt us much. So in here you see the blue line, which is the normal training, and the red line, which is the quantized training, and they're the same. We train a neural network. But the fun thing is that for inference, we get almost this 4 times speed up. So by using the TPU uses in the quantized integers, and the CPU uses the CPU and the GPU use floating point operations, we almost get this 4 times speed up. For just to make it clear, blue and log perplexity are our performance metrics in translation. So blue is a number you want to have high, perplexity is a number you want to have low. And you see that the TPU, as opposed to the CPU and GPU, they kind of achieve the same score. They have the same blue score, they have the same perplexity score. Yet if you look at the coding time, there's a 4 times speed up. Critical people will notice one thing in this table, and in this table our GPUs are actually slower than CPUs. That goes against common knowledge, because this is matrix multiply, so why shouldn't the GPU be faster? And that is because in the decoding, especially once you decode it in production, we have this attention model going on. And that attention model includes like a non-trivial amount of I/O between a given GPU and the host. And therefore, for production decoding, the GPU actually gives a slowdown rather than an improvement. But the conclusion from this table is if you use quantized integers as opposed to floats, we get this 4 times speed up. So to conclude the talk, we motivated natural language processing, and we said, hey, what is deep learning doing there? Recurrent neural networks form the backbone of many of these algorithms, so we discussed it, and also the sequence-to-sequence layout, because our input sentence might be of different length than our output sentence. Then we discuss how do we train them. We use these word vectors. We train them. We train them fast using data parallelism, model parallelism, and for inference, we can quantize our states in order to speed up the translations. That was my talk. I'm happy to take questions.